Morning. Everyone's got a maximum of 10 minutes. If you're not finished in 10 minutes, we're going to move to the next presenter. We have to do it like that. We've got stats to get in. So I'm going to give you an 8-minute warning. Okay. After 8 minutes.
Okay. I've only got six slides.
Yeah, absolutely fine.
Right. So can we put the first slide up?
Yeah, just give us 1 second. Your time hasn't started yet, Roger.
Thank you. Right, okay. You've changed the font, but that's fine. Okay, so I'm going to talk. Sorry, I should perhaps explain very briefly that I'm a private consultant in the UK. Background is mostly building physics and HVAC, and what I'm going to talk about is a specific aspect of the sort of things you're talking about. So in particular, it is very problem orientated. My background is much more in applied research than university research, so it's about trying to solve a particular problem as simply as possible. So if we can go on to the next slide. Well, okay, so the issue is that where a heating system is operated intermittently, as most of them in the UK are, or at least with night setback, the vision is to have a method that depends only or very largely on in-situ measurements to come up with the sizing of the system, or more specifically, the relationship between the warm-up time and the power of the system. Can you go down to my next slide? I can only see my title slide. That's it. Okay. So the basic principle is that if you know the cooling down curve for, say, overnight cooling, and the shape of the warm-up curve when the heating first comes on, and you know how those scale with, for example, temperature difference, empirically, if you know those two, the shape of those curves, you should be able to deduce the relationship between the warm-up time and the power purely from those curves, which can be obviously be measured empirically, so which that sort of overlaps with quite a lot of things you've been talking about. So we go on to the next slide. Okay, so the reason we want to do this is that there are currently two basic ways of sizing systems. The old traditional one is to calculate the design heat loss and apply something called the plant size ratio, which is just a multiplication factor. That's been used for over 100 years. It's never had any logical scientific basis. People have complained ever since it was first introduced that it's essentially a matter of guesswork and thinking, well, this worked last time, so we'll use it again. But if you start to look at the physics and what's happening and the sorts of things we've just been talking about, you realize that actually it's not likely to be reliable in well-insulated dwellings. And the few occasions I've seen of comparisons with empirical data, it doesn't work very well. So it's risky. The other approach is to use simulation, which brings us back into the issue of how good is your data? What do you know what you've got to start with? It also, even the most complex simulation tools make a lot of simplifications, like the air temperature is uniform. Usually ignore the contents of a room. And again, there is no, at least if there is, I haven't seen any convincing empirical validation of this sort of modeling when you get a step change of heat input. Most of it is to do with consumptions and sine waves and things like that. So there's questionable. I'm not saying it's wrong. We don't know. So what we're looking for is an empirical alternative to doing this. So if we can move on again. The advantages, I think I've more or less said in the last slide, which are you use as found thermal response. It's nice to know the response factors, but actually, if you can extract from the application of the response factors rather than the response factors themselves by just measuring the cool down shape, the shapes of the curves. That simplifies the what you need, the information you need. Okay, let's move on to the next slide. So where am I at the moment? So this is something I'm doing off my own bat. So I'm not being funded to do this, but it comes about because it's important for system sizing, and it goes back to some work I did in the early days of simulation in my research career, where we never got to the bottom of it. So I have developed the logic already for some idealized assumptions and convinced myself that I can see a structure which might work. There are two immediate questions. One is, how well do these curves scale with temperature? Which probably quite well, one would imagine, but also, and this must overlap with a lot of the work you're already doing, how consistent are they across different patterns of weather and use? In other words, does it matter when you obtain the information, or can you just go in at any time of year and do it? If that works, then there's the question of applicability and quality control and all the rest of it, which is the sort of thing we've just been talking about. So finally, I'll go to the last slide. Where am I at the moment? First thing we need to do is, as I say, test scalability with temperature, and Rich and his colleagues have very kindly offered to make some of their test house data available, which is really good because it's sort of realistic, but also under situations which are very similar to the assumptions that are usually made, which may not be very realistic, but at least you know where you are. So that's the first step. And then the next step is this question of consistency between over time, basically. And I'm pretty sure that I can get information from some other existing work, which will allow me to at least have a first shot at doing that. And I imagine that some of the things that you guys are doing would also overlap with that. So basically, that's what I am proposing to do. I think it basically relates to your subtask 4, though of course you can't avoid then going on to questions of data collection and curation and quality control and the like. And that's it.
Excellent. And under time as well, Roger. So a bonus point for you. With regards to the work that Roger's doing, I'm presuming he'll be joining Subtask 4's work, but obviously Roger's details are there as well if you want to drop them behind and have a chat with him. Excellent. Thank you, Roger. If you can stop sharing. Oh, no, we'll stop sharing, should I say?
I don't think I am sharing.
Much, Roger. Cheers. Colleague. Okay, Nuria, would you like to put your camera on and your microphone, and we can share your slides, or you can share your slides? It's up to you.
Yes, can you hear me? Yes?
Yeah.
Okay, I'm going to share my screen. Wait a moment. Can you see the presentation? Yes?
We can, and I presume everyone else can as well. So, Nuria, I'm going to give you 10 minutes, and I'll give you a warning when we get to 8 minutes. So it's over to you.
Okay, thank you. So, well, first of all, my name is Nuria Sanchez, and I am a colleague working with Maria Jose Jimenez and also José Alberto Díaz, who is going to present also today part of his work. So first of all, I would like to thank you all for giving me the opportunity to present this work at this meeting